Now, this question given us the two particles with the same kinetic energy and want us to find out which particle is more suitable to use to observe this nucleon. This is a typical value for the diameter of the nucleon. Now, first thing we see is the kinetic energy. It shows that the particle is not relativistic. That means we can use the classical formula p squared over 2m, the kinetic energy. So from here we know the p is equals to square root of 2mk, and the Bovely wavelength tell us this h over p. We substitute this thing inside, we get h over square root of 2mk. Now we solve for this alpha particle first. So the wavelength of alpha particle is equals to h over square root of 2m alpha k. Now m alpha is approximate the 4 times of the mass of a proton. Now we substitute a value inside. This is a Planck constant. Uh, 2, 4, and the mass of a proton. Finally, the kinetic energy. This is 25 mega. Mega is 10 to the 6, and we have to multiply with 1.6 10 to the negative 19. Convert this thing into the joule, the unit joule. So from here, this I get this is a 2.87 10 to the negative 15 meter. Now the same thing we solve for the wavelength of this proton and the same formula but different mass, so 2mpk. We can copy this whole thing to here, but now we only have one proton, so we don't need to multiply with 4. Here I get this is 5.73 and 10 to the negative 15 meter. And now we do the ratio of this lambda over this the diameter of nucleon. So for the first case, this alpha particle, I get this is 1.2. Now we do the same for the wavelength of a proton. This one should be round off. So here this is I get this is 2.4. Now you can see that means the wavelength of the alpha particle is closer to the diameter of a nucleon compared to this wavelength of a proton. So we can conclude that the alpha particle is is better in re- resolving the detail of the neutron. So this is the answer for this question.